All right, next we're going to take a look at a specific example of computing a power of a matrix. So we're given a matrix A, although we need to work out what its entries are, and then we're asked to compute the cube of A. And we're going to do it in two different ways. First, we're going to do it using direct multiplication in the sense of just directly applying the definition that we just talked about on the previous page. But then in part B, we're going to take a look at it from a different point of view, which is going to turn out to be really neat. So first of all, what's the matrix? So A is a 2 by 2 matrix that rotates vectors in R2 by pi over 2 in a counterclockwise direction. Well, that's a specific case of the matrix we just talked about, right? This is what you would use for A for rotating vectors about the origin by an arbitrary angle theta in the counterclockwise direction. But in our case, we want to do it specifically by pi over 2. So that tells us how to get the matrix A in this example. So let's write that out first. So A is going to be, well, I'll just replace all the occurrences of theta in the previous formula with pi over 2. And then we can figure out what our matrix, our rotation matrix in this example is going to be. So once you evaluate all these trig values, what you end up with is the following. You get 0, 1 for the first column, and then negative 1, 0 for the second column. So that's the matrix whose power we want to compute. So for part A, well, A cubed, by definition, this is A times A times A, right? And it may help to think about it this way. I'm actually going to just write it, instead of writing it like that, I'm going to write it as A times A squared. And then it's evident that, well, first we need to compute A squared. So why don't we do that down here? I'll start a new line, and we'll work out A squared as follows. So A squared is going to be, well, here's a copy of A, and then we're going to multiply it by another copy of A. And you can work out this product of two 2 by 2 matrices, just computing one entry at a time. So let's do that now. For our first entry up here, I'll multiply this row by this column to get this entry. And what will that give me? 0 times 0 plus negative 1 times positive 1. That's going to give us negative 1. And then if I multiply this row by this column, that will give me this entry here, which is going to give me negative 1. 1 times negative 1 plus 0 times 0, so that's going to give me negative 1 again. And now work out the other two entries. I'll leave it to you guys to do that as an exercise. Multiply this row by this column to get this entry, and multiply this row by this column to get this entry. And what you'll find is that they're both 0. Okay, so that is your copy of A squared. So let's go back up and continue on from up here. Ooh, I didn't give myself very much room, did I? I'll slide down a tiny bit. So I'll have another copy of A, because we're multiplying A by A squared here. So that's A, and then the A squared is the one we just worked out. Okay, so that is what we need to compute. So now we have another matrix product. So, okay, well, again, we're going to work out each entry one at a time. So the result is it's a 2 by 2 multiplied by a 2 by 2, so the result is going to be another 2 by 2. Let's figure out the entries. So I'll start by, I'll do different entries this time just to be different. So I'll work out this row and this column multiplied together to compute this entry. So what's that going to be? 0 times 0 plus negative 1 times negative 1. That's going to give us positive 1. And now if let's say I multiply this row by this column, that's going to give us this entry. So we'll have 1 times negative 1 plus 0 times 0. So that's going to give us negative 1. And then, again, the other two entries, you're going to multiply this row by this column to get this entry. And then you're going to multiply this row by this column to get this entry. And again, you can check that. I'll leave it to you to check that they're both equal to 0. So that is our product, or our power, which is still a product, but it's also a power, A cubed. Okay, so that is worked out as requested in part A, just through direct multiplication. Notice we had to do two matrix products just to compute A cubed. What if it was A to the power of 4 or 5 or 6 or 7 or 17? You can start to see really quickly, powers are no small ask. It's for someone to compute, and this is just for a 2 by 2 matrix. Imagine if it was, say, uh, a 9 by 9 matrix. There's a lot of calculations involved in computing a power, and you could very quickly wind up in a situation where you have to spend a lot of time, energy, and paper just doing a whole bunch of arithmetic calculations just to work out a power. So powers are something that we take very we want to be very cautious when we ask someone to compute a power by hand. And it turns out there are more efficient ways to compute powers in matrices, and we'll see some of them in this course. But for the moment, we just need to see how it works and make sure that the concept is understood. But I'm sure you can appreciate now already that powers are a complex operation to evaluate in the matrix world. And really, it comes down to the fact that matrix multiplication is a complex operation. It's not as simple as just addition, subtraction, and scalar multiplication. Those are much less demanding. Okay, so what are we looking at in part B? Determine a cube by considering it as a composition of transformations on R squared. Well, remember how we identify a matrix with a linear transformation through multiplication. And we've talked about well, it's 2 pages ago now, we've already seen too that if we compose two transformations, so we write out a composition of, say, a transformation T and a transformation S, the standard matrix of that composition is the product of the two standard matrices of each of the two factors. So powers of a matrix can be interpreted as a composition of a linear transformation with itself. Let's take a look at that in more detail, and I'll show you what I mean. So let's start part B. So I'm going to draw some axes here, and we're going to need actually 8 of these to fully get the point across, so I might as well draw them now. Oops. Well, there's nothing. Actually, how about I just do this? Okay, so here's what's going to happen. Here's what we're going to do. We're going to view a cubed as a linear transformation. Okay, we're going to view it as the standard matrix of a linear transformation. And based on how we can figure out what standard matrices are, if you understand the transformation, you can figure out what the standard matrix is by just applying the transformation to both of the standard basis vectors. So that's what we're going to do. So let's think of A. First of all, let's keep it simple. Let's start with just A as a linear transformation. Well, what would we do if we wanted to, if we reviewed it as a linear transformation and you wanted to know what it would do to the standard basis vectors, what would you do? Well, we know what it does, right? It rotates vectors in the counterclockwise direction by pi over 2 about the origin. So if you were to, here's what we're going to do. We're going to apply A, then we're going to apply A again, and here's where the cube part comes in. We're going to apply A as a linear transformation 3 times, and we're going to see what it does in the end to the standard basis vector E1. So what is it going to do in the first case? Well, if it rotates it counterclockwise by pi over 2, you're going to get this. Right? That's what it means to rotate that by pi over 2. Now what if we do it again? Let's apply A again and rotate it by pi over 2. Well, that's going to take you over here. And this is going to give you A squared of E1. You've applied the transformation A twice. So we've got A times E1. Now, so that I'll draw the rotation arrow as well. Okay, and then we're going to do it one more time. If I rotate it pi over 2 in the counterclockwise direction one more time, that's going to bring us here. And this is going to be our, oops, I can do that. A cubed E1. And that's going to be our third rotation. By the way, what are the coordinates of that vector? It comes down to the coordinates of this point here. Well, we know that the standard basis vector is of length 1. The arrow, the line segment that forms the arrow is of length 1, and it's pointing directly down, so you can tell right away its horizontal component is 0 because it's pointing directly down, and its vertical component is -1. So now we know what A cubed does to the standard basis vector E1. And you might have noticed already, I don't want to get ahead of myself here and spoil the surprise, but notice that that's exactly what the first column of A cubed was. Let's do the same thing now for the second standard basis vector. So I'll draw a picture of E2. Okay, so we've got E2, and what would A do to that vector? Let's apply A, then we'll apply A again, then we'll apply A again. And that's the third application of A. So that's where the A cubed part comes in, remember. So what happens if we rotate the vector E2 by pi over 2 in the counterclockwise direction? That will bring us down here. Right, so this will be A E2. And then if we do it again, well, that's going to bring us down here, pointing directly down. This is going to be A squared of E2. And then if we do it one more time, that's going to bring us over here. And now this is our A cubed E2. And that's, you can recognize this. If we think of it as starting here, although we actually started at E2, but you're going all the way around to the base of the initial place that E1 was, if you didn't rotate E1. Right? So you know the coordinates of E1, it's going to be 1, 0. And hey, that's also kind of familiar. Look at that. A cubed of E2, that happens to be the second column of A cubed. Really, why did it work out like this? Well, we're just viewing A cubed as a linear transformation and then working out its standard matrix. So what are you going to get if you treat it as a linear transformation and then work out the standard matrix of that transformation? Well, you're going to get the matrix who you were trying to interpret as a linear transformation in the first place, which in this case is A cubed. So it's no surprise that that happened. So in this case, let's pretend this was from the context of having never even done any of this. Imagine this stuff wasn't here. Okay, I'm going to delete it just for the moment, but I want to bring it back. But what this tells us now is this tells us what A cubed is. Just from thinking about what the matrix A does to vectors, that was enough. We can work out A cubed just by thinking about it as a composition 3 times of the transformation that is achieved by multiplying a vector by A and thinking about what A does. Let me hit backspace here before I forget. So we could just put these columns together now and use that to figure out what A cubed is. So that's what it means to do part B. So let me just write it out thoroughly here. So A cubed can be obtained with its first column given by A cubed E1 and its second column given by A cubed E2. So that's going to give us 0, -1 for because that's what we got up here. And then the second column is going to be 1, 0 because that's what we got over here. Okay, so that is how we can compute powers by interpreting the base, which is the matrix A in this case, as a linear transformation and viewing powers as just repeated applications of that transformation.